the first speaker is Joerg Polzehl.
That's a bad place.
And this is about quantification of noise in magnetic resonance imaging.
So what I'll be talking about is a very practical problem that we had to solve in the context of our analysis of especially diffusion MR experiments. And what I plan to do is I will talk a little bit about the physics behind the early stages of modeling in the context of MR in order to explain the problem. And then I will give example we speak about the problems, especially in low signal to noise ratio data in this context. I will provide a solution, or at least a partial solution to the problem, and then I will conclude with examples where I show how this solution improves results. Okay, let's start with MR. So what you have to think about is such an MR tomograph. So that's a very strong magnet, usually 3 Tesla, and you have the patient or subject lying in here, and then what's observed in principle is spins of water molecules and of, let's have, hydrogen protons. And what's going on is you have a strong magnetic field here, and then there's an additional magnetic field gradient applied, which causes the water protons to get out of direction, so they spin around the z-axis. And what's recorded is how after this additional magnetic field gradient is put off, the spin or the water molecule goes back into the direction enforced by the large magnetic field. So you observe a signal that's has a real and an imaginary part. In principle, what you do is you record slices consequently to get a 3D result, and recording the slices goes line-wise, so that you have, let's say, 256 times 356 array of values, and inside the line there is a certain resonance frequency which corresponds to the location of the signal that you are interested in. So this encoding frequency that changes along the line. Okay, so the measurement is in a so-called K-space, and the measured signal in K-space, which corresponds to signal decay and phase information, this is normal, complex normal with an expectation xc and a variance sigma squared k, which can be assumed to be more or less homogeneous. The image itself is produced by fast Fourier transform. So fast Fourier transform gives a complex signal again, and you have an expected value, you have Gaussian distribution, and you have variance sigma squared E for image space. And then, unfortunately, what most MR scanners do automatically is they turn a complex signal into a magnitude signal using the phase information. And what you end up with is a signal, SE, with a distribution, SE divided by sigma E. It's distributed chi-squared with 2 degrees of freedoms and non-centrality parameter eta E. And this eta E corresponds to the expected value or to the modulus of the expected value of the signal distribution. Otherwise, in the single coil or single receiver coil system that we have here, you are in the situation that SI follows a so-called Bayesian distribution. The problem that you face is that the expected value of the signal is larger than the non-centrality parameter times sigma E. And this difference is especially severe if sigma E is large. So in the case of small SNR. The situation gets more complicated if you are looking at multiple receiver coils. Multiple receiver coils is what's used in all modern MR scanners. So you have 8 to 32 spherical arranged receiver coils where the magnetic signal is spread out. You have inhomogeneous coil sensitivities, and you have correlation between the observations in the different coils. So what you have to think about here is for an 8-coil system that the signal deteriorates if you move away from the receiver coil. And you need a reconstruction algorithm in order to produce the final MR image. The easiest way to do so is the best studied image reconstruction method is sum of squares. It's nice because it leads to a known distribution. That's simply a chi-square distribution with 2 times number of receiver coils is degrees of freedom. But it has a location dependent sigma E due to correlation between coils, and what is more severe, it's inefficient, and that's why it's not used in practice. Okay. The most common used method is Grappa, introduced by Prisman in the end of the 90s. Here you have so-called encoding matrices, which combine coil sensitivity information with the transformation matrices from fast Fourier transform. So you do a reconstruction in K-space in this form, and you get an efficient image reconstruction, but with a complicated distribution of the signal. The signal is only approximately chi-squared with degrees of freedom and non-centrality parameter depending on location and depending on encoding matrices. And of course with correlation. So that's rather difficult to analyze. Would be nice if you knew the encoding matrices, but that's also something which we usually don't get out of the scanner. Okay, and then there's a third, very nice method for image reconstruction proposed last year by a group from the MR Institute in Minneapolis. And this is reconstruction based on a complex image signal. So we have here the color sensitivities mainly, and this leads again to a Bayesian distribution for the signal, and interest here and two signal depending on color sensitivities and correlations.
This weights CIT, where they came from?
They are the site of a calibration experiment that's done inside the scanner, and again they are not usually not performed. Otherwise you can simply calculate the parameters, but also you don't know the correlation, the two correlations between the coils, and there are several things which okay, the application we are mainly interested in here, because where this problem is severe, because you really have low SMR situations, is diffusion. And diffusion MR is a method that probes on directional information in the white matter area of the brain. So what it measures is water diffusion along an additional diffusion gradient direction. And water diffusion in the brain is mainly restricted by anatomical structure. So in the white matter region, you have fiber bundles going in different directions, connecting different areas in the cortex. And so that's a method in order to analyze this anatomy and describe it by anisotropy information of water diffusion. Okay, the object of interest here is the so-called diffusion propagator. That's the probability density of a particle or spin to travel from a position tau r prime to r in a certain time tau, given gradient in direction r. This is usually aggregated, the information is aggregated over so-called voxel or volume elements, leading to the ensemble average propagator. And the small p is the initial probability density of the particle diffusion. Okay, how does this correspond to the signal that's observed? So the diffusion gradient is, there's a Fourier relation between the non-centrality parameter in the signal distribution and this diffusion propagator. This theta 0 would be the non-centrality parameter in case of no additional diffusion gradient, and this is the attenuated signal due to diffusion. So principally, we have frequency encoded all the particles that were in a certain position in the beginning of the experiment. Due to the gradients, they move away and back, and a certain proportion returns. And so we measure how the ratio of water protons which are in the original position of the bits. The easiest model here is the diffusion tensor model, and this assumes a exponential decay driven by a so-called diffusion tensor. So it's, in principle, it assumes Gaussian diffusion in the diffusion propagator. So here you have a diffusion tensor di, you have gradient direction g, and strength, so that's normalized, and the strength of the gradient is put in V.
Is B also dependent on I, on the location?
No. G and E are determining the image that you get in a single experiment. So usually what you do is you apply different gradient direction, and you may also apply different gradient strengths. This would be the so-called multi-shell experiment. Okay, and in order to characterize the diffusion tensor, you are looking at rotational invariant measure, the fractional FA, which tells you something about the anisotropy, and you are looking at the eigenvectors, or at the largest eigenvector, which tells you about the main direction of diffusion. Okay, so what is the problem with Lewis and we are in a situation that so usually people are using the incorrect nonlinear regression model. They replace the do a regression using the expected value. For a Schei distribution, it's a distribution on the positive axis. The expected value of the signal is larger than the signal of interest. So you have two effects. One effect of variability is that you have a spread of eigenvalues in the estimated diffusion tensor, which is SNR here is always measured for the non-diffusion image. So all other images are deteriorated with respect to this. And then there's a second effect, and this effect is a bias that's introduced due to replacing the SI by the non-centrality parameter by the signal. So that's a homogeneous situation. This is a situation where you have anisotropy, so you have one large eigenvalue and two small eigenvalues, and you see the bias here. You see the bias here. Okay, effect of B-values. What you see is in case of low diffusivity, so that's when diffusivity is restricted by anatomical barriers, and then you have a slow deterioration, still a signal which is far away from the noise floor. If you are in a situation that you have larger diffusivity, that's usually along the fiber directions, then what you see is that as soon as you go for higher B values, the signal becomes almost undistinguishable to noise, and the error that you make is you replace the non-centrality parameter, which is down here, by the expected value of the signal. Okay, if you look at FA for different values of B, then you see that you have an overestimation of FA for small SNR. In case of low B value, that's mainly an effect of variability. And the situation becomes more and more worse if you increase the B value to 7,000 in D, where the main effect is bias. Okay. So we have seen there is a severe variance of estimates and there is instability. In case of low SNR, we have in two situations. One is high B values, and the second one is high resolution imaging. The background is that SNR is proportional to voxel volume. if I reduce the volume of a voxel in order to see smaller structures, I immediately reduce S naught, and the problem becomes C. Correct modeling in order to avoid these bias effects would mean to use likelihood or to use some quasi-likelihood where you replace the true signal by the expected signal given the true variance. And here weighting with the variance of the signal. Doing so requires a correct assessment of sigma and Li, the number of degrees of freedom, the number of effective points.
Yeah, so the sigma, is it treated here as a nuisance parameter or just some sort of values?
That's a parameter of the distribution.
So sigma,
And the goal will be to estimate this sigma from the data.
so sigma is also a parameter.
Sigma is
Even target parameter.
not here. Here, when estimating the diffusion tensor, which is included in this D and V, when estimating the diffusion tensor, then this is a parameter I need to describe the distribution. So it will be a two-stage procedure, estimating sigma from images, and then using it in producing the estimates. Okay, so let's come to estimation. We make the following assumptions. We assume that the signal is Schein distributed with 2L degrees of freedom. So we assume that we know L as in sense 1. And the non-centrality parameter theta I divided by sigma I. This theta I, so the signal, is assumed to be local constant, which corresponds to signal corresponding either to tissue or to tissue and fibers going in a certain direction. And the second one is that sigma I is, so we have seen local homogeneity there. And the second main assumption is that sigma I slowly varies in space. And that's due to the sensitivity profiles, so the C in the reconstruction algorithm, or the encoding matrices varying slowly in space. And then what we have constructed is a sequential multi-scale algorithm using local weighted likelihood estimates for theta I and sigma I, and a robust median smoothing in order to stabilize the estimated sigma I. And weighting schemes, they are localized in image space and adapted in parameter space. So the principle you have to think about is you have an image like this, probably with a little bit more noise, and you have a variance that varies spatially, very smoothly, with a maximum usually in the center, and the spread between lowest variances and maximum variances can be something up to scale, factor of scale. What's usually done is the sigma is estimated from the background, so the border region, which UDM estimates and doesn't give a picture. There's one exception. There's a method proposed last year by Bayer Fernandez, which also takes population into account and which somehow leads to an inhomogeneous estimate. Okay, that's the algorithm. I will be very short here. So it's an initialization then you compute weights. That's a usual adaptive weights scheme. If the sum of weights is larger than some N0, then you estimate zeta e and sigma e by weighted log likelihood. If not, you have an identifiability or at least a high variability. Otherwise, you keep some initial, usually global estimate of sigma, and you simply estimate the parameter theta by moment estimate. And then, if again the sum of weight is large enough, you do a median smoothing. And median at that point, because you can't expect that these estimates here are very good in all locations. There are certain locations in the image where these where the weighting scheme doesn't really describe the homogeneity of the structure. So what we want to do is here use a smoothing procedure that has robustness properties.
Yes, so this LE parameter, is it given?
LE is assumed to be known.
Is it really I-dependent?
If you are dealing with grappa, it is. If you are dealing with sense 1, or if you are dealing with sum of squares as a reconstruction method, it's not. Then it's a global.
But in each case it is known.
In each case, it's not.
And so this N0, what it is typically?
That's a parameter of the algorithm.
What is typical value?
So we usually use 2.
2. So this is a big value.
You should use something smaller.
Yeah,
Certainly not something less or equal to 1.
Definitely not, but always 2 is also.
So, just some examples. So that's a simulated example, which is built on this original image. So we have added noise in K-space with a sigma K ranging from 50, 100 to 800. So that's a very noisy image here. Very low SNR.
It's homogeneous noise.
No, it's added in K-space, and we have sensitivity profiles, which are not constant, and we have correlations between coils. So the sigma itself is like this. So it ranges from 0.86 times sigma k to 2.73 times sigma k. And what you see is the relative error of the local estimates for one size. So everything which is green or near to green has a very slow relative error. Everything which is blue or close to red has a large error. And for comparison, so that's our results. For comparison, these are the results by performance 2013. And that's the best known method. Okay. So if we look at the sensitivity with respect to parameters, what we see is, so there are several parameters in here. There's an adaptation bandwidth lambda, and we see that the results are not uniform over lambda, and especially not uniform over different SNRs. So the different colors here correspond to different values of sigma k. And smaller values of lambda provide good results, in case of large SNR, and you should use a little bit larger or small, but still you get reasonable results usually for a value of number with 5. Second is the bandwidth of the median filter. And here it looks like if you increase the bandwidth, at least for our smooth situation, this still increases or decreases the relative error. The third one is the number of iterations, and again, you have usually small improvement if you continue to iterate. So our proposal that we use is 1 or 5, bandwidth for the median equal 5, and K star equal to 5. Okay. Next problem that we have seen is variability of the estimates. And in order to address this, we recently proposed a method for adaptive smoothing. The problem with this method for adaptive smoothing of diffusion weighted MR data, so that's adaptive smoothing in differential geometric group, is that again here, in order to specify the distribution, you will need an estimate of sigma. Up to now, we used the global estimate, and now we are in a situation to replace it by a local. So that's a result obtained, color-coded FA map obtained for the original data. Here, the image intensity corresponds to FA, and the color corresponds to the direction of diffusion. If we use on this data, and that's a data set with where we have 28 non-diffusion weighted images and 240 diffusion weighted, we get an estimate of sigma like this for the non-diffusion weighted images, for the diffusion weighted images. These two images, they characterize the relative error of over the 28 and over the 240 images. With these relative densities. These relative densities here, they also include variation between the different images, and so that's an overestimate of the relative error. Okay, if we apply this together, we get an, so that's tensor estimates based on smooth data using the estimated sigma in the smoothing algorithm and in the estimate of the tensor. This gives a very nice homogeneous result. If we use a global estimate of sigma in the smoothing algorithm, then the problem is you get a nice result in some areas. In some areas you don't really access the homogeneity structure in the data correctly. And so there's quite a lot of improvement here. This is the result again that you get for the tensor model using the correct description. What we have here on the right hand side are the differences in FA value between the correct model, in this case quasi likelihood, and the incorrect regression model, so there's quite difference. Okay, and that's simply the references I used. So there's a very recent document last week about this local estimation of the noise level in MRI. There's one of the papers for adaptive smoothing of diffusion data, and there are several papers.
Thank you. That's nice. Plate. Area questions. So there was some question again, but so I just try to, especially for our specialist again in semi-parametric estimation. So here is a nice area where can be where actually not only theory but also approaches are very relevant, because here the Newton's parameters are known volatility, local volatility is extremely important. Smoothness, so it's extremely high dimensional, and what only helps is the smoothness assumption about this local volatility and local noise level. And what is of course missing, still missing here, is a nice theoretical justification. So therefore it could be a nice topic for theoretical study as well, and also for probably for some proposals. Because actually the procedure which is applied, it's not EM algorithm, it's something rather adaptive weight with some ideas from EM procedure incorporated. So
I would say the ideas from different field settings.
yeah, so I mean, I find it's very fascinating. So just try to draw your attention. It's a nice real application which requires a real theory still. Okay, so thank Joerg once again, and now the next talk.